Okay, so we've talked about area under the curve, and now we've talked about differentiation. So let's go ahead and see if we can talk about how they relate. So an area accumulation function is a function that describes the area under the curve that is gained or lost as we move from a lower limit of integration to a variable upper limit. So for example, let's look at the function capital F of x is equal to my integral or antiderivative from 0 to x of 2 dt. So there are several things to unpack here. First of all, why do we have dt versus dx as we normally do? In this case, t is a dummy variable. It has no special significance other than to be different than x, because x is the upper limit. So we will see dummy variables in problems where the limits are variable. Secondly, what does it mean to have a variable upper limit? So let's consider several values of x in the context of the function above. So if we are integrating f of x from 0 to x of 2 dt, if we were to integrate, find the area under that curve from 0 to 0 of 2 dt, well, that means I am just trying to find, I'm starting at 0 and I'm ending at 0, which means there's no accumulation of area. So that's going to be 0. Now, if I'm going to be integrating from 0 to my upper limit of 1, well, I want to know what the area of this rectangle is. And I can see fairly clearly that that's going to be 2. If I integrate from 0 to 2, well, then I want to know what the area of this rectangle is. And I can see that that's going to be 4. If I'm integrating from 0 to 3, well, then I want to know what the area of this rectangle is. And I can see that that's going to be 6. If I integrate from 0 to 4, I can see that that area is going to be 8. And lastly, 0 to 5, I can see that my area is going to be 10. Now, looking at this data, is there an explicit function f of x that's not defined as an integral that describes the pattern that we see? Well, we can see that capital F of x is going to be equal to 2 times x. Okay, so let's change the problem slightly. Will the result change? So we're going to integrate from 1, we're going to change our lower limit to 1, and we're going to integrate from 1 to x. So this time, I'm going to try to make sure my colors stay the same. I'm going to integrate from 1, but now I'm going to go backwards to 0. And if I'm working backwards, we're going to use this property. We have the integral from 1 to 0 of f of x dx will equal the negative integral from 0 to 1 of f of x dx. So that means this area will be negative 2. Now, if I'm going from, again, 1 to 1, I can see that my area is going to be 0. And now, if I go from 1 to 2, I have 2. If I go from 1 to 3, I'll have 4. And it's fairly easy to see that if I go from 1 to 4, I have 6. And if I go from 1 to 5, I'll have 8. Now, what is my new function? Well, if I look at that equation, I can see that I'm going to have that capital F of x is equal to 2x minus 2. So similarities and differences. I have a c, which I'm going to describe as my vertical shift of my original function. I also can see that my c is going to be determined So what if we now change the integrand slightly? If we have our capital F of x is my integral from 0 to x of 2t dt. Again, we're going to start from 0, and I can see that my integral from 0 to 0 is indeed going to be 0. If we go from 0 to 1, I can see that my area is going to be 1. If I go from 0 to 2, I'm going to have the area is going to be 1/2. The base of that triangle is 2. The height is going to be 4. So I can see that that area is going to be 4. From 0 to 3, again, I'm going to have, using triangles, I have 1/2 times 3 times 6, which gives me 9. And then lastly, from 0 to 4, I have 1/2 times 4 times 8, which is 16. So does that explicit formula look familiar? It should. It should be capital F of x is equal to x squared. So this is an illustration of the general power rule. So lastly, let's consider this. If we have a situation where b is greater than a, and we know that the integral from a to 0 of f of d dt is our function value at a, and our integral from 0 to b is f of b, how can we calculate the integral from a to b of f of t dt? So let's go ahead and look at that. We have this area is f of a. Well, this whole area is f of b. And it should be fairly obvious to see that this area in between, so the integral from a to b of f of t dt is going to be capital F of b minus capital F of a. This result is called the fundamental theorem of calculus. Interestingly, we can pick any suitable antiderivative of f in order to apply this theorem. In other words, any f of x with any constant of integration. Typically, we choose c is equal to 0, but it makes just the math a little bit easier. But formally, this is the fundamental theorem of calculus, where f of x, capital F of x, is an antiderivative of the function little f of x, differentiable and thus continuous on a to b. Okay, so let's go ahead and take a look at a few examples of these. We're going to evaluate a few definite integrals. So we have the integral from 0 to 4 of 2x dx. Well, we know that the antiderivative of 2x is x squared. We don't need a plus c because we're evaluating it as a definite integral, and we're going to integrate it from 0 to 4. So we have 4 squared minus 0 squared, and that gives us a value of 16. So let's go ahead and take a look at the next example. And we're going to rewrite this as the antiderivative from 4 to 9, or integral of x to the negative 1/2 dx. Increase our power by 1 and divide by that number, so 2x to the 1/2, evaluated from 4 to 9. So that becomes 2 times 9 to the 1/2 minus 4 to the 1/2, which gives us then 2. I'll go ahead and have you finish those two as a question at the end of this video. So, if you want to determine the bounded area for a function that dips below the x-axis, we need to be able to break the given interval into multiple intervals. and either A, subtract the integral for the region below, or then switch our limits of integration. So if we have this function that we're integrating from -1 to 2, I know that the area above the x-axis is going to be positive, while the area below the x-axis is going to be negative. So we cannot just simply say -1 to 2 of x cubed minus 2x squared minus x plus 2 equal to the integral -1 to 2 of the absolute value, because we need to take into consideration the fact that the area below the x-axis is going to be negative. So in this case, we're going to go ahead and separate the integral. So we have the integral from -1 to 1 of x cubed minus 2x squared minus x plus 2 dx. And then we're going to be subtracting the integral from 1 to 2 of x cubed minus 2x squared minus x plus 2 dx. So now we take our antiderivative, and we have 1/4 x to the 4th minus 2/3 x cubed minus 1/2 x squared plus 2x that we evaluate from -1 to 1. And then we're going to subtract, and again, we're going to have the same integral. That should be a 4 minus 2/3 x cubed minus 1/2 x squared plus 2x. And we're going to evaluate that from 1 to 2. As you go through that math and evaluating the fractions, you should get a value of 37/12. So make sure you've got that and understand where that came from.